E dotted with dA over some closed volume gives us the charge enclosed divided by epsilon naught. We've also seen a partial form of Faraday's law. Which is E dotted with dl over a closed path. So this pertains a closed surface. This pertains a closed path. This equals 0 because the electric field has to be conservative, its path independent, energy has to be conserved. So this is a partial form of Faraday's law, and I would like to emphasize this by writing the word partial here. When you talk about electric circuits, then this law is just akin to Kirchhoff's voltage law, KVL. Because as you can well imagine, that this is a potential difference. So if you go around a circuit which is also a closed path, a closed circuit, then the difference in potential from the starting to the final points is 0 because the final and the starting points they just coincide. So around a loop in a circuit, the sum of voltages is 0. So this is what we've been discussing so far. But before I move on to the concept of electric currents, which is going to be our new topic, I would like to talk about just one application of this Maxwell's equation. Now what this equation shows us is that certain patterns of electric fields are allowed and certain patterns are not allowed. They are forbidden. For example, if you have a point charge at some point and we make a hypothetical sphere around it, and if we draw the electric field pattern here, we know that the electric field pattern is pointing radially outwards. This is fine, all is fine so far. But suppose we have some distribution of charges. And if I draw a hypothetical sphere in space, and I propose that the electric field lines or the electric field vectors on this hypothetical sphere are tangential to the sphere. So the electric field magnitude is constant at all of these points at a fixed distance from an origin, but the electric field lines are tangential. So is such a field pattern possible? Is it permissible to have such a field pattern? If we have charges and they are static, they're not moving, and there are no magnetic fields involved because we haven't put magnetic fields into our discussion as yet. Is such a field pattern permissible? What do you think? What's your idea? No, why not?
So it can be because if the sphere is at infinity, the critical field is infinity from that charge.
No, it's not. It's anywhere in space. It's a finite radius. So you can't have an electric field like this. What's the reasoning? Come up with the reasoning. Please, आप बताएं. जी. What do you think? Why? Well, we're not talking about any metals here. It's just space, and we're talking about electric fields. आप बताएं. Is such a field pattern allowed? Why not? Come up with the reason. Saying no is not sufficient. Why not? Please try to be in time, and when you are late, just sit on somewhere as soon as possible. Can anyone come up with the reason why such an electric field pattern is not allowed? Ji. Please stand up, please stand up. Why? Right. Otherwise what? Please complete your sentence. Wait, I'm not talking about any area here. There's no area involved. This is just a path. This is just a circle. I'm not talking about an area. I mean, there's nothing moving here. Even if the charge is moving in a straight line or in a circle, I mean, if the charge is moving with uniform velocity, it's a constant current. The current is not changing, the magnetic field is not changing. Then what? Is such a field pattern allowed? Yes.
So Faraday's law won't work because then you could do E dot L throughout the whole path along that sphere and then
It's not a sphere, by the way. It's a path.
whatever it is.
It's not a sphere. Whatever it is not the. It's not a
But
sphere.
it's closed, right? So it's tangential.
It's a path. It's a circuit. A path. A loop.
Yeah. So then if you try to do E dot L throughout the whole loop, fine, you will have an answer that's more than zero because it has some tangential. Another way to put it is to put an electron there or something and it'll start accelerating forever.
Exactly. So I've just written down the Faraday's law and I've drawn a field pattern and the connection between them is really clear. If I take this point, it's a circle and I go around this circle, my dl and my electric field are always parallel. So the angle between them is 0. This is a constant electric field, so I take this integral, then I get a positive number. And if I get this positive number, it means that this does not hold true. So if I have an electron or a proton, if I put a proton here and the proton is moving around in a circle, it's going to pick up energy because its potential is going to change. Its potential energy therefore is going to change. And therefore it's going to constantly pick up kinetic energy as it moves around this circle. So it's going around and round in a circle and constantly picking up energy, and there is no external source of energy that is pumping the electron or the proton. So I've just written down this Faraday's law and I've drawn a field pattern and I've stated that this field pattern is not allowed if you do not have any magnetic fields involved. Alright? So such a field pattern is totally impermissible. Suppose I have another circle and I draw a field pattern which is neither tangential nor radial, rather it's at a certain angle with respect to the tangent. So at each point I draw a tangent and the angle between the tangent and the electric field is constant. Is such a field pattern allowed? आप बताएं। Right. So each one excuse me, each one of these vectors can be resolved into two components. One component is tangential and the other component is radially outward. So this is a tangential component, a radially outwards component. But the tangential components all around the circle, they're not allowed. Hence, such a field pattern is impermissible, because then the tangential components will not be commensurate with the Faraday's law. So there are certain patterns of electric field inside space that are not allowed because of Maxwell's equations. No matter how intelligently and cleverly you put different charges at different positions, you make up a configuration of charges, the electric field pattern cannot simply exist. Alright, so you cannot come up with a distribution of charges that produces an electric field of this kind or an electric field of this kind, and you would like to keep the charges fixed or stuck to certain points in space. If the charges are moving and they are accelerating, then it's a different issue. Alright, because that's why I've written a partial form of Maxwell's equation. Now I would like to shift gears and I would like to start a discussion on electric current. Any questions? This is a new topic altogether, but it's going to build upon the foundations that we've set up. Any questions? So electric current we know is associated with the movement of charges, with charges having some velocity. Different kinds of electric currents exist. For example, you can have an electrolyte, such as molten sodium chloride, and you have sodium cations and chloride ions inside this medium. And then you insert electrodes inside the medium, a positive electrode and a negative electrode. This is called the anode, this is called the cathode. So if you set up this potential difference inside this bath of molten sodium chloride, the ions will start to move. The positive ions, the sodium cation will start to move towards the cathode, and the anions will start to move to the anode. So there is motion of ions here. Now if you take a hypothetical plane inside this molten solution, and you're sitting on this plane and you're finding out the charge that is flowing through this plane. It could be a membrane, for example. Now how much charge flows through this membrane per unit time? That gives you the current. So the current is through some area. Remember, you should be really confident about the concepts of points and areas. Fluxes pass through areas. Currents pass through areas. Alright. Now if you are on this membrane, you just count the number of charges and their magnitudes passing through this membrane per unit time. But will there be any, if we have connected these electrodes to a power supply, to a battery, per unit time, what's the charge that crosses this membrane? It's the current, but what is the current? Will there be any current flowing through this membrane, to this hypothetical surface? Yes or no? Charges are flowing. But the problem is that positive charges are flowing, say, to the in this direction, and negative charges are flowing in this direction. Yes, there will be current that is flowing through this membrane because positive charges are flowing towards the right, negative charges are flowing towards the left. So this negative charge flowing towards the left is effectively the same as positive charge flowing towards the right. So both of these streams of moving ions constitute a current, and they will add up cumulatively. Their effects will add up. However, if we had a situation in which there was a membrane here and negatively charged ions were crossing this membrane at a certain speed, and positively charged ions were also crossing this membrane at the same rate, then no current will be flowing through this circuit because both positive and negative charges are piercing this membrane. So current really is the amount of charge that passes through some surface per unit time. Positive charges must be taken to be positive here and negative charges must be taken to be negative here. Alright. So this is an example of a current flowing. This scenario represents no current flowing, even though in absolute sense charges are crossing this membrane, but since their signs are of different polarity, they're positive and negative charge, and both of them are rushing to this membrane in the same direction, they will not constitute a current. So the net amount of charge that flows through this membrane per unit time is zero. Now there can be different examples of currents. We have currents through molten liquids, We have the Earth's core as well. So the Earth has three layers. There's the crust, there's the mantle, and there's the core. The core itself has two layers. There's an inner core and an outer core. And there's a certain boundary between these inner and outer cores. This boundary is generally called, if you study a little bit of geology, it's called the Mohovitic boundary. Now, the pressure and temperature is so high inside the core that the material, which is primarily silicon, it ionizes, and then the silicon ions and the electrons, they all flow in the form and they produce convection currents inside this core. So there's current inside our Earth as well. In fact, this current is responsible for creating Earth's magnetic field. This is a theory that is called the dynamo effect. There is current that is associated with lightning. There is current that is inside in our bodies as well. In fact, the first demonstrations of electric currents were made on physiological systems, on frog legs by Alessandro Volta. Nerve impulses, neurons, transmit information in the form of electrical pulses. There's current over there as well. So currents is a very all-embracing concept. And the basic definition of current stems from this idea that you have a membrane or a surface and charges are permeating this membrane, and you find out how many of them pass through per unit time. Now let's quantitatively formalize these ideas a little bit. Suppose I have, and I'm going to focus on metals today. Suppose I have some volume. It could be a metal, it could be some solid, and there are charge carriers. So there have to be charge carriers when we're talking about current. Suppose those charge carriers are denoted by these spheres. They could be electrons, protons, anything. And these charge carriers are uniformly distributed inside the medium. And there are n charge carriers per unit volume. So this is a charge carrier density. And each one of these charge carriers is moving with the same speed. Let's call the speed v, towards the right. How are these charge carriers moving? There is some electric field inside this medium. So these charge carriers, let's assume that these are positive charge carriers. They are moving inside this medium under the action of an electric field because they're accelerating, and they have some speed v. For the time being, we assume that all of them have the same speed, and this speed v is uniform. It does not change with time. So it's steady as well. It's a steady speed, non-changing speed, constant speed. Now, if I would like to find the current that is passing through this medium, so what I really need to do, I could take this surface. This surface has an area A. I would like to find out the current through this area A. Because charges are outside as well. So this is some hypothetical volume inside a larger medium. So this is just some hypothetical volume. There are charges everywhere and all of them are moving with some speed v. Now I just take a cross-sectional area A and I would like to find out the current that's going through this area. Alright. Now if this hypothetical volume has some length as well, so this is a cube inside the medium, I would like to find out how many charges flow through this cross-sectional area per unit time. So this cross-sectional area is inside the plane of the black hole. So my current I has to be the amount of charge that crosses this area. Now could you please tell me what that amount of charge is? So I would have to find out how many charge carriers cross this area per unit time. Now there are n of them per unit volume. So what this really means is that if I have, let's draw a more, I need some more space. So this is my cube inside the medium. All of this is the medium. Remember, there are charge carriers everywhere. This is another cube. And this is just a front view of the cube. So there is an area inside. Alright? So this area is A. Now there are charge carriers here. Now how many of these charge carriers will cross this area per unit time? I know how many of them are there per unit volume. So what's going to happen is that this entire volume is going to drain into this volume per unit time. I need to find out what this volume is, and I multiply that volume by the number of charge carriers per unit volume. I get the number of charges, right? So what's the volume of this cube? So this charge, which is at a certain distance from this cross-sectional area, can permeate into this, across this surface. How far can this charge be from this? If I take a time delta t, how far can this charge be? What's the distance of the furthest charge that can cross this area in a time delta t? It's v into delta t. So this length is going to be v delta t. Any charge that is within this length will cross this area and permeate into a neighboring volume in a time delta t. But the cross-sectional area is A. So the volume of this hypothetical cube is A v delta t. But how many charges are inside this volume? The total charge inside this volume is n times A v delta t. So this amount of charge which is filled up inside this volume has the possibility of crossing this surface in a time delta t. It's just like a fluid flow. This entire volume inside this dashed cube is going to drain into this volume in a time delta t. So all of these charges are crossing the surface area in a time delta t. This is the amount of charge that flows through this area. So current is simply this charge divided by delta t. It's simply going to be equal to n A V multiplied by the charge on each charge carrier Q. Let's call it Q. So this current is NAVQ. Alright. So this is the definition of current. The amount of charge, the number of charges per unit volume into the area through which we're calculating the current, into the speed of each charge carrier, which is assumed to be uniform throughout the volume, into the charge on each charge carrier. If this were an electron, this charge would be minus E, the charge on a single electron. Different materials have different charge concentrations. Bigger the area, bigger will be the amount of charge. Higher the speed of charge carriers, larger will be the current. And I could also do another identification. I can take this A to the other side, NVQ. This is current per unit area. And I can call this the current density, and I denote this by J. So now I have two kinds of relationships for the current and for the current density. Current is through an area, and this density is at a certain point because it's the current per unit area. So you can take this area to be as small as you like. So this is the point function, this is a surface function. Now since the velocity is a vector, So I can put an arrow on top of this. I'll have to put an arrow on top of this. This current density is really a vector. So I have this relationship for the current density. This is something you need to remember, in fact. And you don't remember because of memorization, you remember because of repeated usage of formulas. So this current density J is given by N, Q, the charge on each charge carrier, and multiplied by V. Okay. And the current itself is a scalar, and this is defined as J dotted with, of course this current is this J multiplied by A, but it's really a dot product because area we've taken to be a vector. So this is J dotted with dA integrated over some area, and this is an open area. For example, suppose I have charge carriers that are moving towards the right. All of them have the same velocity and they're moving towards the right. And I take an area inside this medium through which charges are moving. If that area is such that the area vector, capital A, is parallel to the velocity, which means that this area is normal to the flow of charges, then only then charges will be able to cross this area and you will get a current through this area. So current is through this entire area, remember. But how do you find the current through this entire area? You take the current density at each of these points and break up this area into small infinitesimal areas, dAs. Find the current density here, J here, take the dot product of this current density with this infinitesimal area and integrate over this entire area. This will give you the current through the entire area. If I rotate this plane so that I have a plane that is along the flow of charges, then the area vector, the dAs and the area vectors are going to be normal to the velocities. And the current through such an area inside the same medium is going to be zero, even though charges are really permeating, are going through this medium. But there's no current through this area, through this section that we've chosen, because the dot product between the area and the velocity vectors is zero. So that's why the current is defined through an area, is taken to be the dot product and summed up over all these small patches in the area we're considering. Now this is an example of a uniform current. We can have more examples. Suppose Suppose I have a wire, an electric wire that is carrying current, and this is connected onto a printed circuit board on which there is a track that has been laid out or a bus that has been laid out. Now current is flowing through this wire and it has to go inside the bus. Now if I were to look at the charge carriers, they are flowing from the wire to the bus. But at each point I know what the current density is, because it's a vector, it's going to point in a certain direction. So the current density here is in this direction, it's parallel to the wire, but as soon as this junction with the bus arrives, these objects have different conductivities. So, and the current will no longer be, the current density will no longer be along the axis of this bus, it will spread out a little bit. So the current density here is going to spread out a little bit. So these are the current density vectors, and finally far away from this point conductor they are going to become parallel once again. So here the J is totally different, it's not along the axis of the bus. Far away from this wire all the J vectors come parallel to the bus. So you can have examples of currents that are current densities that are non-uniform. So this is an example of a non-uniform J. So if I were to draw a streamline for the current density that represents this scenario, then essentially my charges are flowing like this, then they flow outwards, and then they go inside the bus like this. So these are my streamlines. This is how charges are flowing. It's just like the flow of a fluid through a small orifice, through a small aperture. The fluid spreads out. So the current density J can be uniform, it can be non-uniform, and it's a vector. And remember that this J always equal N Q times V. G. बस क्या है? Follow नहीं हाँ, एक track है. Now with these basic ideas, we have to apply these ideas, and the best illustration of the application of the concept of current is by considering how current flows through metals. Alright? Now consider a wire, a simple wire, an insidious object that we call a wire, and it's carrying current through it. This means that some charge carriers could be positive charge carrier. Let's talk about metals. So let's consider free electrons inside the metal. Suppose current is flowing in this direction, and it's a steady current and a uniform current. So this means that the J vector for this charge carrier is in this direction, and this is the J vector for this charge carrier. Sorry, if current is flowing, conventional current I is flowing in this direction. Now, if I'm talking about mobile electrons, free electrons inside the metal, they have velocities that are anti-parallel to this conventional direction. So there's a velocity vector here, a velocity vector here, a velocity vector here, and a velocity vector here. So each of these charge carriers, and there are many of them, there are n per unit volume, has a velocity vector which I've denoted by these white arrows, v. And I would just like to put a small d here. This d stands for drift, and I'm going to explain this concept now. So there's a velocity vector associated with each electron. And since there's a velocity vector, there is a current density at each of these points inside the wire. Alright, there's a current density as well. So there's a current density here, a J here, a J here, a J here, a J here. So at each of these points there is a J vector, which corresponds to the charge carriers that are moving with a certain velocity at that point. So there's a charge vector, there's a charge moving at every point, so there is a V, D at every point, and there's a J at every point. So I'm representing these current densities by J. Alright, now what we have is a situation that is out of equilibrium, because charges are now moving. They can be accelerating as well. So if I look at this wire, and I take a section A, and I take a section B, then what's going to happen is that I can use Faraday's law, or I can take the line integral. I can find the potential difference between point A and B. If the potential difference between point A and B is delta V, which is VB minus VA, we know that this equals minus the work done by the internal forces, which is the electric field. Now generally in conductors we consider that there is no electric field inside the conductor, but here the situation is different. This electric conductor, no doubt it's an electric conductor, but charges are now flowing. So this is an out of equilibrium situation. There has to be an electric field inside this conductor that allows charges to flow. The electric field will apply a force on the electrons will accelerate, and they will cause the velocity of these electrons to change. The velocity is not really changing for a certain reason which I'm going to explain, but there is an electric field that is set up inside this medium. Alright? Now, this means that this difference is non-zero. Now, if you look at the electric field, if the motion of the electrons is in this upward direction, the electric field has to point in a certain direction. What's the direction of the electric field inside this conductor? Is it from B to A or from A to B? It's from B to A, because the electrons move, they're negatively charged particles. So an electric field is set up inside this wire, in the interior of the wire as well. And that electric field must point in this direction. So now if I draw this wire again, I'm drawing this wire in a slightly bent fashion out of purpose. An electric field has been set up in this wire. This electric field is changing its direction, but it's always axial with this conductor. Right? So if this wire bends, the electric field also bends. But at each point there exists an electric field. That electric field causes a drift velocity of the electrons, which I'm denoting in yellow. And this on a whole causes a current to flow, a conventional current to flow inside this wire. Now I've taken two sections, A and B. And the potential difference between A and B, VB minus VA, is minus E dotted with DL. Now if all of these electrons are moving with the same velocity, that is the velocities are uniform, then the electric field has to be, the magnitude of the electric field has to be uniform. Alright? Because it's the electric field that is creating a velocity. If all the velocities are uniform, the electric field has to be uniform throughout the length of this conductor. So the length of this electric field vector is the same as the length of this electric field vector. So the electric field is uniform. Remember this word uniform. Uniform is with respect to space. So if this electric field here is uniform, I can take this out of the integral. And the electric field is always, so I'm going from A to B, so I'm moving along the axis of this conductor. So the electric field is always parallel to the path that I'm taking. So I can write this as minus E times L, where L is this distance. Now this is negative, which means that VB is smaller than VA, which means that this is at delta V is minus E. Alright, but this is, if the electrons are moving from this point to this point, the path that the electrons are taking from A to B, so the electric field is always anti-parallel to the electric field, this becomes positive. So this is a positive number, which means that VB is larger than VA. This plane is at a higher potential. This plane is at a lower potential. Which really means that there exists a potential difference across this wire which is making the current to flow. So this point is at a higher potential. This is closer to some battery, for example, perhaps. So this is at a higher potential. It is causing current to flow from the high potential side to the low potential side. So inside this wire, whenever the current is flowing, an electric field is set up. Now we have to see how that electric field is set up. But there exists a potential difference across the wire. However, all points on this plane, these points, all of them will be at the same potential. There can be no electric field that exists perpendicular to the axis of this plane, and this is something that comes out from Faraday's law, as I'll explain. Now I would like to take two questions before I move on. Yes?
Sir, is the resistance of the wire constant or is it changing?
The resistance is constant. because I have minus E dotted with dl. Now electrons are moving from point A to point B, so the path that they are taking is anti-parallel to the direction of the electric field. So the angle between these vectors is 180 degrees. So this is a negative number. With a negative number it becomes positive. So whenever I have a wire that is conducting electric current, what's going to happen is that a potential difference is set up at different sections of the wire. There will be a constant potential gradient along this wire which will cause the charges to flow, and there will be an electric field that is set up inside the interior of this wire that is making electrons to flow. Now let's talk about this electric field a little bit more. How is this electric field set up, and how do charges move with the constant velocity? Now this is a very neat concept. So I'll take 15 to 20 minutes on this concept, and then I'll show you a demonstration as well. Remember, this is almost the year 1900 or 1899, and there was an English scientist with the name of Drude. And this was only 3 years after the electron had been discovered by J.J. Thomson, another British physicist. So the electron had been in the news only for 3 years. There was some object called the electron, a particle. And Drude used this concept in its nascent stages to describe how metals conduct. So we're going to talk about the Drude's theory. So it's a remarkable achievement for Drude, just describing electrons as the vehicles for transmission of electricity inside the medium. So what we have in metal, we all know that there is a sea of electrons. There are mobile electrons. They are not associated with any atom because they have been ionized. They were the valence electrons, they were ionized, and there are n mobile electrons per unit volume. This n comes out from the density of the medium, how many valence electrons are available, and the molarity of the medium and its atomic weight, etc. This is something you should be able to find out. How many valence electrons are there per unit volume? That depends upon how many atoms are there per unit volume. That depends upon the density of this medium. Okay? So there are n electrons per unit volume, free electrons. There are other electrons, but they are fixed in position. Remember that this metal as a whole is electrically neutral. It has not picked up any charge. We're only drawing the mobile electrons. Now what's happening to these electrons? Are these electrons just sitting there? No. They're moving in erratic direction. They're moving in all possible directions because of the finite temperature. It's a gas of electrons. So these electrons constitute a gas. Sometimes it's called a sea of electrons. Now if the temperature is capital T, the absolute temperature, could we determine what the average kinetic energy of each electron is going to be? Thermodynamics, modern physics. Yeah, it's just an ideal gas. And these electrons are independent. If T is the temperature, what's the energy of a gas molecule?
3 by 2 K into T.
It's going to be Kb, which is the Boltzmann constant, 3 by 2. Because there are 3 degrees of freedom, the electron can move in the x, y or z direction. With each direction there is associated half kBt of energy. This equals half mv squared. But this v is the RMS speed. So half mv squared is the root mean square speed of these electrons. And Kb is the Boltzmann constant, T is the temperature. Higher the temperature, higher will be the speed of the electrons. So in a gas of electrons, all of these electrons do not have the same speed. So if I draw a probability distribution in which I have a speed here and I have some probability here, or the fraction of electrons that are moving with a certain speed, I get something like this. This is called a Boltzmann distribution. This means that most of the electrons will have some speed that lies here. The average speed lies somewhere here. And there's a speed in between which is called the RMS speed. that lies somewhere here. So this is the RMS speed, the root mean square speed. And how do you find out the root mean square speed? The root mean square speed simply means that I take the speed of the first electron, square it. Then I take the speed of the second electron, I square it. I take the speed of the third electron, I square it. I take the speed of all the electrons inside the system, I square them, add them up. Root mean. Okay, after I add them up, I divide by the number of electrons, then I take the square root of this quantity. This gives me the RMS speed of the electrons. In the process of averaging, I will add them without taking the squares. But the root mean square means I take the square, I take the mean, and then I find the root. So this is a root mean square quantity. Okay? And by looking at the distribution, we can find out what the root mean square is. So from Boltzmann's equations, we can find out that the average speed or the root mean square kinetic energy is going to be equal to 3 by 2 kVt. Now higher the temperature, higher will be the speed of these electrons. Now what direction are these electrons moving in? There is no electric field applied as yet. Okay, I'll come to this question. But suppose the temperature is 300 Kelvin, room temperature. If I put in the value of the Boltzmann constant, the mass of an electron, Vrms turns out to be about 10 raised to power 8 meters per second. Oh sorry, 10 to the power 6 meters per second. This is 1,000 kilometers per second. So electrons inside this metal are moving at a tremendously high speed of 1,000 kilometers per second. It's 1% of the speed of light almost. But the point is that these electrons are moving in random directions. So they're moving with extremely high velocities but in random directions. Alright, so if I look at a single electron, I focus my gaze on a single electron inside this metal. It's moving with an exceptionally high speed, but that speed is changing all the time. So this electron is moving with an exceptionally high speed. This arrow now shows the trajectory of the electron. The speed is 1% of the speed of light, really high. Then it sees some ionic core inside the metal. The metal must have ions as well that are fixed in their position relatively. And when it collides with the ionic core, it scatters, it changes its direction. And then it scatters in a different direction and starts moving with a high speed again. And then it keeps on changing its direction. So this electron is actually showing erratic motion in all possible directions, even though the speeds are really high. Now if we focus our attention on all of these electrons, each one of these electrons has a trajectory that is what is called a Brownian trajectory. It's moving randomly in all possible directions. So there is charge, each charge carrier is now moving with a relatively high velocity, but these velocities are all pointing in all kinds of directions. So there is really no current flowing inside this medium because the velocity vectors, when added up vectorially, they will give you 0. So even though this mobile of sea of electrons is highly agitated, it's very agile, it's moving about at tremendously high speeds in all possible directions, the current through this medium is 0 because the sea of electrons cannot move as a whole. It just remains where it is. So if I represent this sea of electrons by actually a sea, since there are many electrons per unit volume, there are 10 raised to the power 22 electrons per cubic meter for a general metal. So this sea of electrons is just represented here as a continuum of charge. It remains where it is because all these velocity vectors, they add up to 0. because they are vectors and they're pointing in all random directions. There is no direction to this motion. So what happens is that no current can flow through this medium. Now what if we have the same metal and now we apply an electric field E. Now each one of these electrons is going to experience a force. What's the direction of the force that each electron experiences? Towards the left or towards the right? Towards the left. So each electron now experiences a force towards the left. So this is the force on each electron, Fe. Now there is a certain effect of this force. This force will tend to accelerate the electrons. Alright? Now each one of these electrons is going to move, is going to preferentially move in the left direction. Okay? Let me draw this diagram in a more illustrative fashion here. So I have a metal, no electric field is applied. So if I draw the velocity vectors for the electrons, they are all pointing randomly in all possible directions at an instant of time. So I'm drawing this diagram at some frozen point in time. So these electrons are all pointing in random directions. And the vector sum of all of these velocities is 0. So this represents the vector sum or the average. The average is just the vector sum divided by the number of electrons. So this is 0 here. No electric field is applied. Fine? So far so good. Now we take the same metal and remember that neither of these electrons is static. Each electron is moving at an exceptionally high speed of 1% of the speed of light at room temperature. Higher the temperature, higher will be the speeds. Okay, remember that. Now we take the same metal and apply an electric field in this direction. Now what's going to happen is that each of these electrons is going to experience a force towards the left. As a result of this, each one of these vectors will slightly shift towards the left. So if you take a picture of the same scenario, which is impossible to do, at the same instant of time, each one of these velocity vectors is going to slightly shift towards the left. Because now the acceleration is towards the left, because there's a force on each electron. So if I draw these vectors that are slightly shifted towards the left, this is what they will look like. So this is just an exaggerated picture of what's happening here. Sorry. Each one of these velocity vectors is going to nudge, slightly tilt towards the left, because an acceleration has been added in the left direction that changes its velocity in the directed left direction because of the electric field. So still, if you look at these vectors, they are all generally pointing, they look like they are all pointing in the random direction. But now if you take the vector sum, it's not going to be 0. Because on top of this random Brownian motion because it's just like motion of pollen grains that's suspended in a fluid. So in the absence of electric field, there was the Brownian motion of electrons, totally random, the average velocity turned out to be 0. But now what we've done, we've applied an electric field, and as a result, all of these velocity vectors have slightly nudged themselves in the direction of the acceleration, which is opposite to the direction of the electric field here, because we're talking about negatively charged particles. So this vector sum is no longer 0. So as a result, this sea of electrons is going to move as a whole. It's going to accelerate as a whole towards the left. This entire C will displace towards the left. So this was the original position of the C, and now if the electric field is applied, this entire C is going to displace itself towards the left a little bit. And this speed is not the same as, this new speed is not the same as the thermal motion of the electrons. It's going to be a different speed, and that is called the drift velocity. Let's see what that speed is. So it's the entire sea of electrons that is majestically moving left or right. It's not the individual electron, it's the entire sea of electrons. So if we get our electricity from Tarbela, it's not the electron from Tarbela that is traveling all the way from Tarbela to our classroom. It's the electrons that are present in these wires, and the entire sea of electrons is moving. And the information from Tarbela to our classroom, that is a new electric field, is set up locally in these wires. That travels at the speed of light. I'll have more to say about this. So now this entire sea of electrons majestically moves left or right under the application of electric field, under a new velocity which we would like to determine. So if the electric field that is applied is E, what we already know is that the electrons will accelerate. Each electron will accelerate. Suppose that acceleration is A. We know that this is F over m. But F is minus E over m. Alright. Now each electron is moving with some velocity Vi. It's the initial velocity of an electron. So when an electron makes a collision with an ion, with an ionic core, so there's an electron that makes a collision and starts moving in a new direction. So the velocity at the point of the collision where the scattering takes place, I call that the initial velocity, right? So this initial velocity is a large number. It's of the order of 1% of the speed of light. It's a really large number because of the thermal motion of the electrons. So this initial velocity plus the acceleration into the time will give me the velocity of an electron at some time. This is a vector, this is also a vector. So the velocity of an electron at some time is given by this. But there are many electrons inside the system. So now what I would like to do, I would like to take the average of both of these sides. Okay? So this is for one electron. For one electron I have some initial velocity at the point of the collision, the acceleration under the action of the electric field, and the time since the last collision. Okay? So my Vt is equal to this. Now I take the average over all the electrons and I denote my average by this sign. So this is the average velocity of all of the electrons, the average velocity of initial of all of the electrons plus the acceleration of all of the electrons. What's the average acceleration of the electrons? Is it the same? Are all electrons moving with the same acceleration? Yes. Into the average of the time. So I can take this, pull this out of the average sign because the acceleration for each electron is the same. Each electron is experiencing the same electric field. Okay? Now what's the average initial velocity? The average initial velocity is 0 because these velocity vectors are all pointing randomly in all kinds of directions. So this is 0. So this average, I just call it Vd, the drift velocity of the sea of electrons. It's the drift velocity of the sea of electrons. Because it is only this drift of the sea of electrons that is causing a current to flow. So this drift velocity Vd equals At. Now A is E over m. And the average time between collisions, I denote this by tau. This is the average time between collisions. Now let's look at this relationship here. The drift velocity of the sea of electrons is minus E, capital E, which is the electric field, tau over m. Tau is the average time between collisions. Alright, so there's some average time of collisions. So when one collision occurs, what on average is the time before another collision takes place? And it's not going to be the same, but there has to be some average. That is called tau. Now let's look at this relationship. V drift velocity equals this. Whenever there is drift velocity, which is a constant here, even though the electrons are accelerating. So now what we have is we have undirected motion due to temperature for the electron, but on top of that undirected motion we've added a tinge of directed motion, a slight pinch of directed motion, a slight nudge of directed motion because of the electric field. ठीक है? तो एक छोटा सा इसको इसकी अनडायरेक्टेड मोशन को छोटी सी एक समत मिल गई इन इलेक्ट्रॉन्स को, और उस समत की वजह से एक ड्रिफ्ट वेलोसिटी प्रोड्यूस होगी. दैट इज नॉट द सेम वेलोसिटी एज द थर्मल वेलोसिटी ऑफ द इलेक्ट्रॉन्स. So this drift velocity is given by this relationship. Let me finish because I'm slightly short of time, I'm sorry. So this drift velocity is proportional to the electric field. And we know that the current density J equals N E Vd. Now Vd is given by this. So I put a minus sign here, E square tau over M E. So whenever there is current density inside a medium, that is current is flowing, there has to be an electric field inside the medium. Without an electric field, current cannot flow. So even though in static conditions there is no electric field inside a conductor, in dynamic conditions when there is current flow, for example, there has to be an electric field that is set up inside the conductor. And that's a different question how that electric field is set up. But there is an electric field. We'll talk about the origins of this electric field in the next lecture, but there is an electric field. That electric field causes a drift velocity, that drift velocity causes a current density which causes a current really. And this object here is called the conductivity, sigma. So J equals sigma E. The current density is in the same direction as the applied electric field. This object is the conductivity. The resistivity is the inverse of this conductivity. So the conductivity is defined as N minus Ne squared tau over M. In general, if I'm talking about arbitrary charge carriers, it's N Q squared tau over M. The charge carriers could be free electrons, they could be anything. Higher the average time between collisions, higher will be the conductivity, which means that the collisions are sparse, they are not as frequent. So less frequent collisions, less frequent scattering events of the electrons with the ionic cores means a higher conductivity. Higher charge carriers that are available per unit volume means a higher conductivity. So different materials have high or low conductivities depending upon these factors, but these relationships are entirely general. And temperature has a very important role to play. So what I'm going to do now is I'm going to show you a demonstration, but before I show you a demonstration, it seems actually a nice idea to derive the Ohm's law. So I have a metallic conductor through which a current is flowing. Now this, I forget about these vector signs because both of these are parallel. This J is really I over A equals. Now I forget about, now I call this the conductivity, which I over A is sigma E, right? Which means that I is sigma A E. But what is my electric field? The electric field is related to the potential difference between 2 points and the length of this conductor. So I have sigma A, the electric field is the potential difference divided by L. Now what I have is delta V equals I L over A 1 over sigma here, right? This is I rho L over A. Conductivity is just the inverse of the resistivity. Now what's this? The potential difference between the ends of a wire equals the current times this object, which depends upon the dimensions of the object, the length between which we measure the potential difference, and this is just the resistance. So we have, in a sense, derived Ohm's law from first principles. Now in the last 5 minutes, I'd like to show you a really nice demonstration that we've built. And this actually shows the temperature dependence of resistivity. Now what we have here is a wire that is connected to a power supply, and the wires feed into an electric bulb which is derived from a motorcycle. It's a 12-volt bulb, and there is a bunch of wires inside this tube. So the wires go in, they loop in here, they form a bunch here, and then they are connected with this bulb. Now what I'm trying to do here is I'm going to connect this to a power supply. I'm going to turn on the power supply. I'm going to turn off the lights. The bulb is not lit up. Alright, it's only slightly lit up because the voltage is not sufficient. I've applied a voltage of 7 volts. It's not sufficient voltage which could drive a sufficient current to light up this bulb. Now what I'm going to do, whenever a current flows through the filament of the bulb, it heats up. Now I'm going to show you an example of heating by cooling something. So what I'm going to do, I have a canister of liquid nitrogen. So this is liquid that is at 77 kelvins, minus 196 degrees centigrade. So I'm going to put this circuit inside liquid nitrogen, and I'm going to see what's going to happen. So I just put this rod, this entire circuit, and I'm going to dip it into liquid nitrogen. And now if you focus on this bulb, please. Let's see what happens. ये कनेक्शन नहीं टूटे बल्ब पे. ये कनेक्शन मुझे लगता है टूट गए. कनेक्शन टूट गए मुझे लगता है. मैंने इसको हिलाया तो this bulb has actually lit up. When I dip this bulb inside liquid nitrogen, it's lit up, and it's lit up quite strongly. Just by cooling the wire, I've lit up the light bulb. So at 7 volts at room temperature, if I had the wire at room temperature, this bulb was almost extinguished. The glow was very feeble. Now I dip this circuit inside liquid nitrogen, the bulb just lights up profusely. So what I've demonstrated is an example of heating something, which a filament is actually being heated up by cooling. Now, can anyone explain why this phenomenon takes place? What's the origin of this effect here? Anyone else? Can anyone raise his or her hand? Why is the bulb lit up when I dipped it inside liquid nitrogen? Anyone from the back? Anyone else? Yes. Kiski internal resistance? Exactly. So as I cooled the wire, the resistance of the wire dropped. And why did the resistance of the wire drop? The resistance dropped because the tau that I have drawn here goes down. The average time between collisions goes down. The average time goes high. The collisions become less frequent. So the average time between collisions goes high, the conductivity goes high, the resistivity goes down, and the resistance goes down. And when the resistance goes down, the voltage is still the same. The current through this circuit goes up, and that current is now large enough to light up the bulb. So this is an example of a thermodynamic apparent conundrum in which I'm heating something by cooling. But that cooling is in fact coming up because I'm vaporizing more and more liquid nitrogen as I dip this circuit inside this cryogenic fluid. Now if I take this bulb outside the nitrogen, lights are on, kar do. This bulb is slowly going to diminish with time, and I can increase its diminishing by heating this. So it's going to diminish with time, and I can decrease the luminosity by actually heating this up. So I can use a hot air gun to heat this up. And finally, when this circuit comes back to its room temperature, it's going to diminish almost completely. The voltage is still on, and you can see the glow has almost disappeared. Alright, so today I have uploaded a homework. That homework is due next Wednesday. Next Friday we're going to have our second quiz, and I'm going to talk about some interesting applications of this stuff. So remember that the concepts that I'm covering, they're quite unconventional. So you have to come to classes. There's no excuse not to come to classes. And mind you, your attendance will have an effect on your grade. Alright, thanks a lot.